All right, hello and welcome to day 5 of Unit 4. Today is going to be slightly different because I am asking that for those of you who don't typically print the notes off and take notes along with me, that you do look in the description down below, in the description is a link to the same PDF file that you could typically print off from Blackboard. But this way you can sort of just open it in a browser and have it next to you. But I will not be able to write the problems on the whiteboard and have enough room to do the work. Okay, so I am asking that you provide for yourself the problems by clicking on the link in the description or going to Blackboard and printing them off like everyone else. Okay, so let's go ahead and get started. Today we're talking about optimization, and basically what optimization is taking some scenario, some situation, and then using sort of the first derivative test to find a maximum value or a minimum value. Okay. So in the first problem, it's about a farmer, and this farmer lives along a straight river. Okay. And he wants to build a fence along said river. Now, this fence only needs 3 sides because it's along a river. Okay. It has a width, it has a length, okay. And the farmer has 2,400 feet of fencing. Okay. My goal is going to be to optimize the area of the fenced-in pasture using only 1,400 feet of fencing. Okay. So the first thing I want to do is understand the problem, which I feel like we do. Draw a diagram, which I already have, and then choose appropriate variables for unknowns, width and length. Those make sense. Now write an equation for the quantity to be optimized. Okay. The quantity to be optimized is the area. Okay. And the formula for area is length times width. Now the problem with this is if I were to start taking the derivative of this, I've got too many variables. Okay. I got too many variables. I need my area function to be a function of a single variable. Okay. So we're going to write a secondary equation involving the quantity or the information that I was given. Okay. The length of this fencing is W plus L plus W, or 2W plus L, which needs to be 2,400 linear feet. Okay. Now, to me, it seems like it's easier to solve for L, so that's what I'm going to do. Now, substituting L in here, I get a simple function. Oops. Okay. And this is a function for the area, and the independent variable is W. Okay. So let's go ahead and expand this. We get 2,400 W minus 2W squared. All right. Now, if we think about what this looks like, it's a parabola that opens downward, right? Okay. And it's been shifted up 2,400-ish, something like this. It's going to be a large parabola. And what I want, since this curve now represents various areas versus the width, I'm looking for the maximum area. I want that point. What's the maximum area that I can make? Okay? And in order to do that, I'm just going to use the fact that the first derivative, okay, when it's equal to 0, gives me that maximum point. So let's see, the derivative of A prime is 2400 minus 4w. Okay, setting that equal to 0, I get that 4w is equal to 2400. Okay. So w must be equal to 2400 over 4, which is 600. I don't know why I had to look. Okay. So that's the width, but what's the length? Well, I can go back over here to solve for the length. And I solve for the length and I get 1200. Okay. So that's my answer. The question was, what's the width and the length? What are the dimensions of the fence that give me the maximum area? Well, those are the dimensions that give me the maximum area. If I wanted to solve for the maximum area, I could simply take my W and plug it back into here, and it would tell me what range value I get out of this function. And I'm not sure what that is, but that wasn't the question. The question was, what are the dimensions that yield the largest area? Okay. And I guess we need some units on there. They're linear feet. Okay, hopefully by now you've got the problems in front of you. As you could tell with the last example, it's very difficult to follow along if you don't have the problem in front of you. So I do need you to open up that file and be looking at the problems as we go along. Take the time to read the problem to yourself and try to understand it, and then we'll walk through it together. Okay. So the next example is about a box. Okay. So we have a box, and we want to make this box out of a flat piece of cardboard. Okay. So here's my flat piece of cardboard. Okay. And it has dimensions 30 by 16. Okay. Now to turn this into a box with an open top, right? We'll keep it this way. I'm going to cut out squares from the corners. Okay. With those squares cut out, I now have something where I could fold these flaps along the dotted lines, and I could fold those flaps up and get a box that looks something like this. Right? And then how do you open the box? You just draw a line over there. Right? So my goal here is to take a flat piece of cardboard, cut out the corners so that I can fold it up and make a box. My cardboard has some given dimensions, and what I want to optimize is the volume of the box. So the thing being optimized is volume. Oops. volume. Okay, well, volume is length times width times height. Now again, that's a function of volume of 3 variables. And this isn't multivariable calculus. This is single variable calculus. There's no Lagrange error bound, or there's no optimization using multiple variables in this class. Okay, so we need a single variable that we can use to represent the volume here. So let's go back to this flat piece of cardboard and let's give a variable to the thing that is changing, the thing that we're trying to figure out how big to make it, right? And that's these little squares here. We want to know how big should these squares be, or how small should they be in order to optimize this volume. Okay? Well, all of these squares have a length of x. Okay? So now, if you can imagine folding these pieces up and folding these pieces up, the height of my box is x, right? Because all I've done here is taken this back flap, which used to be laying flat like that, right? I folded that up and I folded that up to create the box, okay? So the height is x, okay? The width here is this, which is 16 minus 2 x's. And the length here is 30 minus 2 x's. So now I can substitute those values in for length, width, and height. So see, volume is now a function of a single variable x. The length was 30 minus 2x. The width is 16 minus 2x, and the height is x. All right, now we're going to go ahead and expand this, and notice you should get a cubic function, right? Okay. And that cubic function that you get is, let's see, 480x minus 92 x squared, so plus 4x cubed. Okay. That's what I want to optimize. Now this does have, it's going to have a max, it's going to have a min. So I might get 2 values and I have to determine which one is the best possible match, okay, based on the problem. So let's go ahead and find the first derivative of v. The first derivative of v is going to be 480 minus, was that 184, double check, 184 x plus 12x squared. Now this I can simplify a little by dividing out 4, and then when I set it equal to 0, I'll have a 3x squared, and I'm just switching the order around so that it's easier for me to see. That's a plus 120. So all I've done from here to here is divide out a factor of 4. Okay? And now I have a quadratic that does in fact factor. Okay? Okay? And this is going to factor to something like 3x minus 10 and something like x minus 12. Right? 10 times 12 is 120. What is that? 36 and 10, 46. Okay. So that does factor, and I get 2 values of x. One value of x is 10 over 3. The other value of x is 12. Now, one of those values isn't going to work. Let's see. If x were 12, then this cardboard that is only 16 inches wide, a 12-inch cut up this way would go over halfway, and this cut down would go even, over halfway, and so 12 doesn't work. So it's got to be 10 over 3. Okay? So let me try to explain that one more time. If x were to be 12, hypothetically, 12 plus 12 is 24, which is larger than this side that I've been given. Okay, I'm only given 16 inches on this side to deal with, so 12 is far too deep a cut. So there's no way that the cuts could be 12 by 12. They've got to be 10 thirds by 10 thirds. So that's my answer. Okay. Now, what's the maximum volume? Well, you could find that out by taking that and plugging it back in here. But that's not what the question asks. The question asks, what value of x, or what size cut, gives me the largest volume? That's it. Okay, we're going to switch gears here, and we're going to look at something a little more abstract, not as concrete, not as applicable to the real world, something a little more conceptual. Okay, so if you read the question says that we're going to be finding, the point on the parabola y squared equals 2x. Okay, that is closest to the point 1, 4. So, draw a picture. Okay, my parabola is going to look something like this. Okay. The point 1, 4 is somewhere here. And I'm looking for the point along this curve that is the closest distance to that point. Okay. So I'm looking for an xy coordinate. I'm looking for an xy coordinate on this curve that is the closest distance to the point 1, 4. So I am optimizing distance. And distance is the square root, the difference in the x's, squared, plus the difference in the y's, squared. Alright? And so this is the distance between 2 points, these 2 points. So we're gonna have the distance is x minus 1 squared plus y minus 4 squared. But I got 2 variables. I can't do anything with 2 variables. I need 1 variable. I need one function. I need a function of 1 variable. So I'm going to solve the equation that defines the curve for x. And then plug that into x. And then we want to differentiate that. No, that's a mess. I don't want to differentiate that. I don't want you to have to differentiate that. So what I'm going to say is, it's not what I'm saying, it's true, is the distance d is minimized at the same point, or the same value of x, or the same value of y in this case, okay, as the squared distance. Okay, so we're going to actually minimize the value s, which is d squared, which is y squared over 2 minus 1. Okay. Minimizing s happens, that minimal point happens at the same place as the minimum point of d, or of d. Okay. So this is what I want to minimize. So what I'm going to first do is I'm going to simplify this. S is equal to, what is this? Y to the 4th over 4. What is it? Y to the 4th over 4 minus 8y plus 17. Okay. And now when I find s prime, I get the 4's cancel and I get y cubed minus 8 plus 0. I want to set this equal to 0. So y must be 2. So s is minimized at 2, and d is minimized at 2. Okay. So when y is 2, what did x have to be? 2. I wanted to see if somebody was going to say out loud in their room, 2. So this is the point on the curve that's the least distance from the point 1/4 that's not on the curve. I am prepared to answer questions about this tomorrow, because I'm sure that leap of faith there I'm going to have questions about. And trust me, I have a better explanation than the one that I just gave you. So. Alright, so for the last example, something a little more challenging. So we got another river, and as usual in calculus, our rivers are straight. Okay. We've got a man standing at A, and he wants to get to B. Okay, through a combination of rowing and running. So he has a few options. He can run directly across the river to this point C, okay, which the river is 3 kilometers, okay, and then he can run all the way down to B, which by the way is 8 kilometers. Or he can do a combination of and run directly to a point D, or excuse me, row to a point D and then run the rest of the way. Or he can row directly to B. Okay. Now we're going to assume that the force of the river is negligible, and so that doesn't affect how fast he rows given the angle of which he departs A. Okay. But what we do know is that this man can run at a speed of 8 kilometers per hour, and he can row, okay, at a speed of 6 kilometers per hour. Now, what am I trying to optimize here? I want to optimize the time it takes him to get from A to B. Okay, I want the least amount of time. The least amount of time it takes him to get from A to B. So he can row directly across and then run all the way down, or he can row directly to B, or he can do some combination of. If he does some combination of, then that point D has some distance from C. Let's call it X, which makes D to B 8 minus X. Okay. So we have to calculate the time he's running and the time he's rowing. Let's do rowing first. Okay. So the time it takes him to row. The time it takes him to row, we can get from the equation distance equals rate times time. Okay. So the time it takes him to row is equal to the distance that he rows over the rate at which he can row. The distance he rows is this distance here, okay, which is just the hypotenuse of a right triangle that has legs of 3 and x. So it takes him, time to row is the square root of 9 plus x squared over the rate at which he rows, which is 6. How long does it take him to run? Same formula. Distance equals rate times time, and the time it takes him to run is the distance he has to run divided by the rate at which he can run. The distance he has to run is 8 minus x. But you say, what if he rows directly to C? Then the distance is 8. Well, true. Then x is going to come out to be 0. Right? And then the distance he runs is just 8 minus 0, which is 8. But we want to account for the fact that he might not be rowing directly across the river and then running. He might be rowing to some point between C and D and then running the rest of the way. So the distance that he runs is 8 minus x. So the time it takes him to run is 8 minus x over the rate, which is 8. Now, I want to calculate the total time, okay, big T. And big T is just the sum of the two little t's. So big T is the square root of 9 plus x squared over 6 plus 1 minus x over 8. Now that's what I want to find the derivative of. That's what I want to optimize. The total time. Okay? So let's see. T prime is 1/2 times 1/6 times the derivative of the inside is 2x and the derivative of the outside is 9 plus x squared to the negative 1/2. The derivative of 1 is 0 and the derivative of a constant times x is just that constant, and this constant happens to be 1/8. Okay. Now we want to set this equal to 0 and start simplifying some things. Right, I get x over 6 times the square root of 9 plus x squared minus 1 over 8. Now it becomes fairly simple to solve, right? Because I can just add 1/8 to both sides. And cross multiply. Okay, divide by 6. Boom, boom, boom. We're going to get 9 plus x squared equals 4 over 3x squared. And we square both sides. We get 16, and you keep solving this, you will end up with x is equal to, what is it, 9 over the square root of 7, okay? So to end that, it's just algebra from here to here. You're just solving for x. Okay? So let's wrap that up. What does that mean? That means in order to minimize the time it takes for this man to get from A to B, through a combination of rowing and running, he needs to row to a point D that is 9 over the square root of 7 kilometers away from C and then run the rest of the way. That will minimize the time it takes him to get from A to B. Okay. So that's it. I know this was tough. We'll talk about it again tomorrow, our next class. Thanks for tuning in.